Welcome to the Deep Dive. This is where we take a whole stack of information, pull out the really important nuggets, and basically give you a shortcut to being properly informed. Today, we're diving into some pretty interesting material. It's a set of practice questions for the JN0-481 certification exam. Think of it like getting a peek behind the curtain of modern networking, understanding the core ideas and the tools that make our digital world actually work.
That's a great way to put it. Yeah, this deep dive isn't really just about getting the answers right. It's more about understanding the why. Why these solutions work, how all the different bits fit together to build these really robust automated networks. We'll unpack some key stuff. Things like EVPN.
Right, Ethernet VPN.
Exactly. Allowing layer 2 over IP. And BGP, of course.
The internet's routing engine, pretty much.
The workhorse, yeah.
Yeah.
And definitely Juniper Apstra, which is a big focus here.
Okay, let's get into it. For anyone curious about the exam specifics, it's 65 multiple-choice questions. You get 90 minutes. It's run by Pearson VUE, and it covers Apstra version 5.1 and Junos 24.4 specifically. Right, let's jump straight into what makes these networks tick. Why should you care about these details? So, building these kinds of networks, you first need a way for devices to, well, find each other, right? Share information, which brings us to EVPN route types. The material asks, which two are used to advertise MC and IP bindings? And the answer points to type 2 and type 5.
Yeah, and what's really interesting here, I think, is how these route types are basically the language the network uses. Type 2 routes, they carry the specific VC address and IP address for individual hosts.
Yeah.
So that's essential for just, basic endpoint discovery, finding who's where.
Okay, the individual device level.
Right. Then type 5 routes, they kind of zoom out, they advertise IP prefixes. This is for routing between different VXLAN segments, so handling the layer 3 connectivity across the fabric.
So type 2 is local discovery, type 5 is broader reachability.
Precisely. And this isn't just technical detail for its own sake. It's what gives modern data centers their agility. It lets you scale out, add new services without having to manually reconfigure everything constantly. It's pretty foundational.
The agility engine, like you said. Okay, so we have this complex dynamic network. How do you manage it effectively? What's the main benefit of using Juniper Apstra's intent-based networking approach?
Well, that really gets to a core question, doesn't it? How do you make sure your network consistently does what you want it to do, especially when things change? Apstra's main advantage is its ability to automatically, continuously validate the actual network state against your defined business intent.
Continuously?
Yeah, it's not just a one-time configuration push. It's always checking. It detects drift, deviations from the intent.
And it can fix them?
It can often automatically correct them, yeah, without needing someone to jump in manually every single time. It's about assurance. Make sure the network operates as designed, aligning the reality with the desired outcome.
That sounds incredibly powerful, almost like self-healing. But does it completely get rid of manual troubleshooting or just change the engineer's job?
Oh, it definitely shifts the focus. I wouldn't say it eliminates all troubleshooting, especially for weird, novel problems, but it drastically cuts down on the routine reactive stuff. The engineer moves from typing commands to defining the intent.
Defining the what, not the how.
Exactly. You focus on the higher level design, refining that intent, and maybe analyzing the more complex issues Apstra flags. You become more of an architect.
That makes a lot of sense. Okay, let's shift gears a bit. Let's talk foundations. The physical network. When you're designing a Junos-based eBGP underlay fabric, what are, say, 3 key best practices for getting consistent, predictable load balancing?
Right, the underlay. Stability there is crucial. Consistency is really the name of the game. First, use uniform link speeds. All your leaf-to-spine uplinks should ideally be the same speed. Avoids bottlenecks.
Okay, no slow lanes.
Pretty much. Second, configure ECMP equal cost multipath everywhere, on all the devices. This lets traffic spread out evenly across all the available paths. You maximize your bandwidth.
Makes sense. Use all the pipes.
Exactly. And third, try to deploy leaf and spine devices of the same model, same capabilities. It just ensures predictable performance, consistent behavior, easier management. You want every path to be equally good, basically.
Right. Avoid those weird performance quirks.
Yeah, I remember back before we standardized ECMP properly, we were always fighting these traffic hotspots. One link gets totally slammed while others are idle. Getting these basics right makes a huge difference.
That's a great practical point. So those are the design principles. How does something like Apstra help you actually implement and, maybe more importantly, maintain that consistency across potentially hundreds of devices? Let's leap back to Apstra. You've made changes in your blueprint. How do you know they're actually ready to go live? What's the signal in the UI?
Yeah, the visual cue. In the Apstra interface, you're looking for the Stage tab. When that turns green, you're good to go. It means all the checks have passed, the configuration is generated, and it's ready for deployment onto the devices. Simple, but important.
Okay, green means go. So the Stage tab is green. How does Apstra actually talk to the devices to push those changes? What protocols does it use?
It uses secure, programmable methods. The main ones mentioned are netconf over SSH.
Okay, secure command structure.
Right, and RESTconfs,
Yeah.
which is more web-friendly, uses HTTPS. These allow Apstra to not just push config, but also pull state information, manage the devices automatically. It's that move away from manual CLI stuff.
Towards programmatic control.
Exactly, which is essential for scale and consistency, like we talked about.
Absolutely. Now, speaking of scale and making things simpler, what's the role of a route reflector in a BGP EVPN fabric? It sounds like something that helps tidy things up.
It absolutely does. It's all about simplification. A route reflector's main job is to centralize how routes get distributed within your BGP setup. See, in a big fabric, normally every router would need to talk directly to every other router to share routes. That gets messy fast.
A full mesh. Yeah, that sounds complex.
It really is. So the route reflector acts like a central hub. Routers only need to talk to the reflector. The reflector then reflects the routes it learns out to all its clients. Cuts down massively on the number of BGP sessions.
So less configuration, less load on the router.
Precisely. Improves scalability, makes management much easier, especially in large data centers.
Okay, that makes perfect sense for large environments. What about practical stuff, like getting documentation out? If you need a cabling map from Apstra, say for records or to feed another system, what formats can you export it in?
Apstra's pretty good with integrating. For cabling maps, it supports exporting in two main formats, CSV.
Spreadsheet friendly?
Exactly. Good for quick reviews, maybe manual checks, and also JSON.
Ah, structured data, good for automation.
Right. JSON is great if you want to feed that cabling info into, say, an inventory system or use it in scripts. It shows Apstra thinks about the whole life cycle, not just deployment.
That integration capability is definitely key. Okay, let's drill down on another core piece, the VTEP. In an EVPN VXLAN world, what does the VTEP, the VXLAN tunnel endpoint, actually do?
The VTIP, yeah, that's a real workhorse, a critical component. Think of it like a translator or maybe a shipping station at the edge of the network.
Okay.
Its main job is encapsulation and decapsulation. It takes regular layer 2 Ethernet traffic.
Like a standard data packet from a server?
Exactly. And it wraps it up inside VXLAN packet, puts it in a sort of digital envelope with a new address for crossing the bigger IP network.
So it tunnels the layer 2 traffic over layer 3?
That's it. Then, when that packet arrives at the destination VTEP, that VTIP unwraps it, decapsulates it, and delivers the original Ethernet frame to the final destination. It's the magic that lets you stretch layer 2 segments across a routed infrastructure. Absolutely essential for VXLAN.
That makes it really clear. Okay, managing devices. When you're adding devices to an Apstra blueprint, what are the different deploy modes you can assign? Sounds like managing their lifecycle state.
Yeah, these modes give you control over how a device fits into the fabric at any given time. There are three main ones. Ready means the device is, well, ready. It's configured, Apstra knows about it, but it's not actively forwarding production traffic yet. It's like it's waiting in the wings.
Staged, but not live.
Right. Then there's deploy. That means it's fully active, part of the fabric, carrying traffic. Showtime.
Okay.
And finally, drain. This is when you want to take a device out, maybe for maintenance or replacement. Apstra gracefully redirects traffic away from it before you pull the plug, minimizing disruption. It's about careful orchestration.
Got it. Ready, deploy, drain. A controlled life cycle. That makes sense for avoiding issues. And speaking of avoiding issues, what's the main point of Apstra's probe tracing feature? This sounds like a pre-flight check.
It kind of is. It addresses that really important question. How can you be sure your network changes will work before you actually push them live? Probe tracing lets you synthetically test network paths.
Yeah.
You define a source and destination, maybe specific ports or protocols.
Like simulating actual traffic flow.
Exactly. Apstra simulates how that traffic would flow through the network based on the current stage configuration, even before it's deployed. It validates connectivity, checks policies, makes sure the path looks like you expect.
So you can catch problems in the design phase?
Precisely. It helps prevent deployment failures, ensures your intent translates correctly into actual forwarding paths. It adds a huge layer of confidence before you hit deploy, catching issues early, shift left. And maybe here's something to think about. As networking gets more and more automated, more intent-driven like this, how does the job of the network engineer change?
Is it going to be less about the nitty-gritty how of configuring individual boxes and more about defining the what, designing that intent, ensuring the system delivers on it? Maybe something to mull over until our next deep dive.